Swayam Prabha. Digital India. Educated India.
Hi, welcome back to Mechanics and Control of Robotic Manipulator. The last two classes we have seen how to generate a trajectory for a general case. So this particular lecture we are going to see a very specific case, in the sense how to employ those schemes into a robotic manipulator trajectory generation. So for that again we are going to take a same example, which is 2R serial manipulator, and we'll see how the joint space scheme and task space scheme can be visualized with the MATLAB. So for that we are actually like taking you can say two such scheme. So you know, even the joint space scheme can be make it as a synchronous and series, or you call actually like a simultaneous and synchronous. So the other one is task space scheme, we can do the straight line interpolation, or we can take independent trajectory generation. So in that sense we are trying to see first what is the example which is given. So now in this case you can see that theta 10 and theta 1f and theta 20 and theta 2f are given. If even the x0 and y0 and xf and yf are given, we can always calculate these four variables through the help of inverse kinematics. So in my MATLAB code I have written based on the inverse kinematics, however it is not going to restrict that way. So in that sense, so we will first try to see how the joint space scheme can be generated. In the sense, this is the initial position and you want to go this final position, but through the help of joint space trajectory, in the sense theta 10 supposed to go to theta 1f and theta 20 supposed to go to theta 2f. That is what we are trying to do. Even you have already seen in the lecture. So this can be done in synchronous or probably in series. So we will try to see both in, you can say, this particular lecture. So first one is actually like synchronous. So where we are actually like taking the you call initial position and you can say final position of the end effector. Okay. So from there what we can do, we can actually like use the inverse kinematics. Okay. So then we can actually like calculate theta 10 and theta 1f, all those things. So in that connection, so even the initial and final end effector velocity also can be given, because that is what the cubic polynomial all about. If that is the case, we can use the Jacobian, in the sense the differential kinematics we can use, where the inverse differential kinematics we can choose and then try to do it. So since it is a 2R serial manipulator, the system parameter or the geometric parameter or the physical parameter we need to use, which is we call L1 and L2 in this case. So that also we have considered. So now the first case we are trying to find the inverse kinematics. So we know already inverse kinematics based on the you can see the closed form equation. So we have used that equation which we derived in the regular lecture. So from there we can find theta 10 and theta 20. So even I would have written as a, you can say, sub function. However, if I write straight away sub function in the MATLAB, some of you may not be familiar. So that's why I have written explicitly here theta 10, theta 20, then theta 1f and theta 2f. So now what we know? So we know initial and final position of both joints. So now we need to find out the initial and final velocity of each joints. So for that we are taking the Jacobian which we derived in the regular lecture. So now that would be substituted on the initial and final location. So we got J0 and Jf. So based on that, you know already end effector velocities of the initial and final. We can find the, you call theta 1 dot and theta 2 dot for initial and final, which we have written as q dot 0 and q dot f. So once these all known, then what we can do, we can go back to whatever profile generation you want to use it. So since it is one of the demonstration, I have taken as a cubic polynomial. So for that we should know what is we call coefficient matrix A, and we should know the you can say known input as a vector. So here the theta 1 initial, theta 1 dot initial, theta 1 final and theta 1 dot final need to be known for finding the first segment joint space trajectory. Similarly, second joints you can say trajectory also can be generated. So based on that, TC1 and TC2 for the joint 1 and joint 2 coefficients, which is we call you can say A0 1 okay to A31, similarly A0 to A32, that we can actually like calculate. So once you calculate, then we can go to the loop where you are actually like trying to run based on T0 to Tf profile. So the theta 1 and theta 2 can be generated once you know. Since this is a synchronous, so both would be synchronously moving. So in the sense it starts from T0 to Tf, completely both joints are rotating. So in that sense we can actually like write theta 1 and theta 2 just to plot as an animated way. So we are trying to find the forward kinematic model so that your x end effector and y end effector can be visualized, and then you can show in an animated way. For doing the animation, we have actually like tried to take this particular you can say MATLAB code. So we are actually like trying to plot 0 as the origin, then x1 and x2. x1 we can write as L1 cos theta 1, and x2 is nothing but your final end effector point. So that is corresponding to the x. Similarly, y we start from 0 origin, then L1 sin theta 1 is the y1, and y2 would be your end effector position. So based on that we can draw, and I want to actually show the continuous profile how it is generated. So I just added that xj and yj from 1 to I. So when the loop is actually like iterating, it will actually like show the continuous plot. And I want to show what is the initial and final point. So I just added two additional plotting where Rs is the red square will come in the starting point, and the Gp is nothing but you can say G pentagon will, or you can say star will come at the green color at the final point. So and we have actually like run everything, and just to show the animated, I pass and hold off. So in the sense every time it would be superimpose one image to another image, but hold off command is there, so it's look like as actually a continuous motion. Okay. So just to show this, I just go to the MATLAB window, and this is the code which we were actually like discussing. So you can see this is the code. So now if I run this, so what it start? So the x initial is actually like 1 meter, and y initial also like 1 meter. It is actually like somewhere like this, and the final also like this. So now we have not given theta 1 0 and theta 1 f directly. So what we can do the inverse kinematics. So now the inverse kinematics will have two solutions. So we will take one solution which is the positive solution of S2. Okay. So now based on this we can actually like run this code. So then you can actually like feel it what I want to actually like explain. So you can see like now it is starting from here and it is ending. So you can see like it is more like the robo is actually like moving, right. So when I run this, so you can see like the physically the robo is moving, that realization you can feel it in MATLAB animation. So I did not make any video, but still it looked like a video, right, because I made it a superimpose. So the next figure I want to actually like show it. So what is the you can say profile or the trajectory generated in task space and as well as the joint space. The joint space theta 1 to theta 2, you can see it's like a straight line. So that is what we call actually like joint space trajectory considered as a straight line. The profile start from actually like 0 to you can say this is theta 1 0 to theta 1 f. It is a smooth profile, and I did not plot the velocity. Even you want, you can actually like do the velocity profile. So now this is the theta 2 f, this is theta 2 0. So like that we can actually like generate. So even you want to actually like realize further. So only condition is this initial input what we are giving, that should be in the case of what you call in the workspace. So we can actually like see I have given interchange. So the initial point is same, but the final point is actually like slightly modified. So now you can see that this is the initial point and the final point. You can see it, right, it is actually like moving it. So this is what the profile and this is what happening, right. So now this is more and more actually like very clear. So now we will actually like go back. Okay. So go back to the code. So now I am actually like looking at this. Okay. So I am just giving it 0, and this is actually like I am putting it so -1. So now I am actually like trying to give, because your L1 and L2 is 1 and 1. So maximum it is actually like on the circle of radius of 2 meter, right. So that is what the range. Within that you can choose anything. So anyhow, next lecture we would be seeing the workspace generation. So you can actually like feel it, right. It is more you can say beneficial. So you want to see this in a proper shape. So even we can actually like make the boundary. So the boundary we can actually like right now I make it this as actually like commented. So now if I actually like make it, it would be giving a real size, okay, like how it is happening, the same size it is giving, this is the real size, okay. So now these all actually like what you call the joint space trajectory with the case 1 where the synchronous. We'll go back to the slide where the non-synchronous we call in series of motion. So for that what we need to actually like do it. So these all actually like the other plots, okay. So I'll just see the non-synchronous. So the non-synchronous you have to actually like do it slightly a trickier way. So these all the plot which we have already done. So the non-synchronous way it is actually like we call sequence trajectory. So here we call the TT is the total trajectory duration, but now I need to divide that into TF into number of segment, because each joint would be rotating independently. For example, now 10 second I have actually like 2 joints. So I actually like break into 5 second each. So first 5 second first joint will rotate, the next 5 second the second joint will rotate. So that is what we have seen as a sequence trajectory. So that is what we are trying to see. So in that sense the coefficient calculation is same, but what you can see like the T goes 0 to TF. Here TF is actually like total duration divided by 2. So that would be generated. So then the correspondingly the theta 2 would be the same initial, it maintained that. So then you can see the second loop, the final would be maintained for theta 1 and the theta 2 would be move as a cubic polynomial. So now the same way we have done the forward kinematics just to plot, and now we will see the same thing in the MATLAB window which will give more clear. So you can see like these are standard which we have done in the previous code. Only change is, so instead of TF I have taken TT, and the TT and TF why I have made it, because I make it actually like the TF always the segment time. The segment time here is actually you can say TT divided by 2. So based on that you will get the inverse kinematics and all. So based on that you will get the joint space trajectory in 2 way. So if I run you will be very clear to this. So I'll just run this, then you will actually like feel it. You can see like the first joint is rotated, the second joint is rotating, right. So it is actually like little faster. So I'll just make it the pass command probably 100 millisecond rather than the you can say 10 millisecond. So now you can see the first joint only rotate, the second joint is as whatever this theta 2 0 is maintained, okay. The first joint rotated. Once it is reached that final, then it is the second joint rotate, right. So while second joint rotate you can see the first joint remains same, right. So you can actually look at it. So from here, so you can see like the first joint rotated. So that time the theta 1 vary, okay, from theta initial to final. So the second segment, so theta final, theta 1 final remains same, but the correspondingly theta 2 start from 0 to final, okay. So that is what the realization. So now you can actually like want to more clear. So I'll just give random theta 1f. So in the sense, so I just give it probably a different point. So I'll just put it, this is minus, okay. So I'll just show it, this is actually like vertical. So then you can actually like see it, sorry. So you can actually like see it while running it. You can see the first joint only rotating, the second joint remains same, constant. So once it reached a particular location, you can see the second joint rotate, that time the first joint remains same, right. So it is very clearly see that the explicit trajectory generation, but this is not preferred at all. However, so most of the you can say kinematic solvers and all done with this way, individual joint would be move in series. So especially if you go to ROS, we call robot operating system. So I already told in the lecture, these things are all very clearly visible there, okay. So now going back to the slide. So we will see this whatever we have seen is the joint space trajectory can we see in a task space. Even the task space we can actually like see in that case. So x initial and final would be given. Similarly, y initial and final would be given. So this is the initial position and this is the final position. We want to follow this in the sense it's supposed to be followed as a straight line. So the straight line is not assured because x dot of 0 and x dot of f, if it is non-zero then it would not maintain. So we will see that how it comes. So in the sense here you can actually like see. So we are trying to do the first case independent trajectory, in the sense x trajectory and y trajectory we are trying to do it in independent cubic polynomial. We are not doing it a synchronous may, in the sense once you do the x, based on the x y can be generated. No, not like that. Okay. So in that sense we are actually like trying to do this. So here you can see initial and final velocity are given and we have taken the same time, which is 5 you can say second, and L1 and L2 are same. So now we have taken the same A matrix, but Bx and By are the two other vector. Based on that the coefficient what we calculate Tcx and Tcy. So now in that case, so xt and yt, which is actually like written as Tcx and Tcy. So in the sense the x trajectory and y trajectory independently derived. So in order to check, in order to compare, so we have done the inverse kinematics just to see how the theta profile will go. So we have done the inverse kinematics. So now we have actually like use the same plotting command. So we will actually like go to this, the task space trajectory 1. So you can actually like see that. So these are the cases which we have shown in the MATLAB, where initial and final, you can say initial and final of y, and initial velocity of x and y and final velocity of x and y, and the total duration is 10 seconds, and you can say this all we have tried, and the A matrix Bx By are given, and based on the Tcx and Tcy can be calculated, and you got the task space trajectory. Then the inverse kinematics, just for our reference we calculate so that we can do the plotting option. Okay. So the plotting option we have used the same thing. So now if I run, so what you have expected, earlier it was a curved, now in this case it is a straight line which is followed, but the straight line is not assured if the initial and final velocity are non-zero. Okay. So now you can actually like see it. So I will just make it the time duration is actually like higher. So now in that case the delay time is actually like higher. So you can see like it starts from this point and it is supposed to go here. It is trying to follow a straight line because the initial and final velocities are 0. If the initial and final velocity are non-zero, what will happen? You can actually like see it by changing that. Okay. So now in that case you can see that the joint space, you can see like it is not following as a straight line. Earlier case it was followed as straight line. Earlier case the task space trajectory is followed as a curve, but in this case is a straight line, right. So the same way x trajectory is smooth, y trajectory is again smooth. These all we can realize it. So just to show that how the non-zero initial velocity will involve, so I am just saying that only, so the non-zero x is there, which is actually like 0.5 meter per second. So you can see that it won't be straight line, it would be giving a small curve, because it is actually like already having some non-zero initial velocity. You can actually like see that it is trying to follow. However, it is going to at rest, it won't get any residue there, but here it is starting from non-zero. You can see that the profile is actually like invariantly modified. Okay. So that is what you can actually like look at it. So even if I give something like the final velocity of this, I am just giving randomly. So the y final velocity is 0.5 meters per second. So you can see like it is actually like for the x axis it is there. So that's why it is trying to go, and now you can see it is modified because the y final velocity is supposed to be somewhere 0.5 meter per second. So in the sense vertically up. So that's why it starts from horizontal and end with vertical. That's what it is showing. Okay. So now you are actually like I hope you are actually like getting the clarity. Now we will actually like move to the second case. What is the second case? So where the straight line interpolation. So the straight line interpolation, only one modification we can expect. So what modification? So instead of this, so we would be having derived from the x. So you can actually like make only x. So then we can actually like make it y. So based on x. So which is what we have done in a straight line interpolation, if you recall. So if once you know this, so you can see like the x of t is derived based on the x of t, the y of t is come. So in that sense, y dot and all will not come explicitly here. Okay. So now in that sense, this is the inverse kinematics, the standard, and we have actually like the same plotting function we will be using it. So the task space trajectory 2, you can look at it. So this is what the given condition. So the same condition we have taken, and x dot and y dot only, like x dot initial and final only we are taking for the trajectory generation. So then we are actually like deriving the y of t or y. So based on x, so that is what you can see explicitly. So then we are actually like moving to the same thing. So now you can actually like look at the profile, which is actually like going to be very smooth because the y would be given. So now you can actually like feel it. So now even if I give some non-zero initial velocities, so for example I am just taking it, this is 0.5. So now the profile would be, you can say, goes like that. However, you can see the y is not coming, right? So that is what you can actually like feel it. So it is actually like going across the line and goes, because you don't have any you can say case, because we assume that this is actually like followed on the same line. For example, if I take -5, okay, so you can actually like feel it, that would be come on the same line and actually like go. So there is no change in your velocity, only thing this profile has interchange. Okay, that's what you would have actually like felt. So this is what the you call straight line interpolation. Even the straight line interpolation, you want to do it even little more, then you have to bring the you can say x dot and y dot term. These terms I don't want to bring it, not to make much you can say complex. This is sufficient for, you can say, run the code. So even you want to more smoother, so what we can do, instead of, you can say, cubic polynomial for the x, even we can use fifth order polynomial or cycloidal. In that case, the yt consequently will come smooth enough. Okay. So that way we can actually like do it. So I hope you are actually like clear to this. So with that we are actually like ending this particular lecture. The next lecture I would be showing how to generate a workspace with the MATLAB. In that we will see like how the task space trajectory will be having some you can say difficulty and all. So in the sense, we will take a simple MATLAB code, single MATLAB code, including workspace and you can say the task space trajectory and you can say joint space trajectory generation, and we can see the comparison in a simple single short video. So with that, I am saying thank you here and see you in next lecture. Until then, bye.